Okie doke. About that time? Well, good afternoon, everybody. Hope everybody's doing well this afternoon. Hope you're enjoying the quarantine this April Fool's Day. So, a few things to talk about today. One thing is, got your stats quizzes. I hope everybody's quiz is in. And so I've started grading those. I'm going to grade them over the course of today. They take a while to grade, but slowly over the course of the day, you should see grades coming in for Stats Quiz 2. I hope by the end of the day, all the grades for Stats Quiz 2 will be entered. So look for that. Now, we've got midterm number 2 next week, and the midterm number 2 review sheet, it's up on the Canvas site, so you should be looking at that. And now you're probably wondering, well, how are we going to do the test? Because obviously we can't do it in class. So this test will, in general, not be a short answer test. It will mainly be a multiple choice test. And what I'm thinking is, since it's a 40-point test, to have 40 multiple choice questions. Now, if you have studied for the test, like I told you to study for the regular tests we had in class, if you've been studying that way with your note cards, you definitely will do very well on this test, as long as you know all the skills and things. So that is how I would study, okay? But what this means is that, yes, there is going to be some time pressure on the test. I'm not going to forbid you to look at your notes during the test, because if I did that, I know some people would be honest and wouldn't look at their notes, but some people I know would be dishonest and would, and so it's not fair to the people who are honest if there are dishonest people who are cheating. So I want to be fair to everybody, so you're not barred from looking at your notes. Having said that, there is not going to be enough time on the test for you to look up the answers in your notes for every one of them, okay? So if you don't come in prepared, no, you're not going to be able to finish the test. The concern about all of this is people are going to say, well, you said it was open book, open notes, but there wasn't enough time to look it up. Well, that's right. I expect you to be prepared for the test, and I expect you not to have to look it up in your notes, but I wouldn't flunk somebody who did look it up in their notes if you think you can do that. So that's what it's going to be. There's going to be a severe time limit, probably half an hour, I would think, to finish these 40 questions, most of which will be multiple choice. And then there'll be a lot more questions that aren't just straight memorization questions where you actually have to think about it to get the answer than it would be if we were doing the questions in class, because I want to make it so you do have to think about it and can't just read it out of your notes, so that you really do understand the material. So that's what the test is going to be like. Now, on Monday in class, Monday's lecture is going to be a review session. I'm going to do the review session like I do the night review session. So it's going to be a longer class on Monday, because I'm going to do a big review session to help you get prepared for the midterm, which would be next Wednesday. And so we're talking Wednesday, I guess April 10th. Wednesday, is that April 10th? Wednesday, April 8th. Sorry, Wednesday, April 8th. April 8th is when the test is going to be. That means April 6th, Monday, April 6th, we'll have the review session. Now, I know my lectures went over last week on time. Lectures this week, usually I have like essentially 2.5 lectures on correlation, and then the remaining half of the lecture is done. The within subjects variance test is what we do. But I'm not going to break it up that way. What I'm going to do is I'm going to finish correlation today. So it's going to be a longer lecture today while I finish correlation. And then on Wednesday, all it's going to be is we're going to learn a new stats test. Sorry, Friday. I keep thinking it's Monday for some reason. I'm sorry. So today, Wednesday, it's going to be a longer lecture where we're going to finish up correlation. But then Friday is going to be super, super short. The only thing I'm going to post on Friday is the TA is going to make a video about how to do the within subjects variance test. And so on Friday, you should use your calculator. And I have the directions for the within subjects variance test up there on the Canvas site on the front page. Use your stat calculator and those directions. Follow along with the TA on Friday to learn how to do that test. That test will be on Stats Quiz number 3, which will be in a little while here. So mostly you need to worry about the midterm right now because that's coming up next week. Okay, well, enjoyed getting a lot of questions from you over email. Let's talk about, and a lot of you like the picture of Rosie. Here's a new picture of Rosie for today, so enjoy that. And so this is Psych 301, research, design, let's capitalize, design and methodology. Okay. And what we're talking about today is this is correlation part 2, the second lecture on correlation. Remember what correlation is. It's a correlation coefficient, which is what we've been talking about. It is a statistic used to measure the direction and strength of the linear relationship between two variables. Okay, so when you're doing Stats Quiz 3, if you want to know whether it's a correlation problem, you should look for a relationship. What the question will ask is there a relationship between, say, somebody's ACT score and their grades? That would tip you off that you're looking for the correlation. And for the one that we learned the type of correlation called the Pearson product moment. For that correlation, that requires ratio or interval data. All right, now, we talked about how to calculate the correlation last time. We talked about positive and negative correlations. But now we need to talk about a concept that you're going to hear about whenever you read about correlational research, and that is the proportion of variance accounted for. The proportion of variance accounted for. This is the proportion of variance in one variable. Come on. What is this? All right, I don't understand this. One variable that can be predicted from knowing the values of the other variable. Proportion of variance accounted for. The proportion of variance in one variable that can be predicted from knowing the values of another variable. And maybe we should add down here, not the amount of variance that one variable caused in another variable. Okay, it's not the amount of variance that one variable caused in another variable, just the amount that can be predicted. All right, let me try and explain what I mean by this, because whenever you see a correlational study, they'll almost always report, in addition to the correlation, the proportion of variance accounted for. Let's say we're going to play the following game. Let's say that you're competing against other people. We're going to choose an adult randomly selected from the United States. And your job is, that's all you know, is they're an adult living in the United States. Your job is to guess how much they weigh. And what we'll do is we'll do this 10 times. You guess for 10 different people, and you don't see these people. You just know they're Americans, American adults. And we'll do this 10 times, and then when you're competing against other people, what we'll do is you'll take your guess and we'll subtract out the person's actual weight to get like the deviation. Take the absolute value of that so that's not negative, and then we'll add all the deviations up so we can see who had the least amount of deviation from the actual values. That's the person with the least error, so they win the game. Now, if you're playing a game like this, and all you know is this person is an American adult and you have to guess their weight, there is an optimal strategy for playing the game. And there is a particular number that you should guess that will minimize your error. I'll give you a chance to think about what that guess should be. And usually people are puzzled. Well, should you guess 0 pounds? No, probably not. That would be too low. Should you guess 1,000 pounds? No, probably not. That would be too high. Well, the answer is, this number has a name. The name is the mean. You should guess the mean weight of adults in the American population. That will minimize your error in that situation. Okay. Well, now let's make the game a little more interesting, maybe. Now what we're going to do is we'll tell you we've selected an adult at random from the population of the United States. But now we're going to give you another piece of information about them. We're going to tell you how tall they are in centimeters. Now, there's a relationship, as we talked about last time, between height and weight. Here's our graph here. And the correlation between height and weight is about 0.8. And so you can see as people get taller, they tend to weigh more as well. Now, if somebody, when you're playing this game, and they tell you the height of the person, let's say that they're 180 centimeters tall, well, now you can actually do better than guessing the mean. So there's a way to compute the best fitting line through these data points. So we can put the best fitting line through the data points. And then we could use that line to figure out, all right, where does the average person who's 180 centimeters tall, how much do they weigh? And so it'll probably be about, well, there, it looks like about 78 kilograms, I would say. About 78 kilograms is what we should guess. Now, because height is correlated with weight, we can actually do better than guessing the mean. If we know the height, we can make a better prediction because those two variables are correlated. But of course, still our prediction is not going to be perfect. And the reason the prediction is not going to be perfect is that there's not a perfect correlation between height and weight. There's only a correlation of 0.8 between height and weight. Now, if the correlation was 1 between two variables, like Fahrenheit and Celsius temperature, well, knowing the Celsius temperature, you could perfectly predict the Fahrenheit temperature because they're correlated 1. But in this case, where they're highly correlated but not correlated perfectly, we can do a lot better by knowing their height than if we didn't, but of course still we can't be perfect. So now the question is, how much of the variability that's in height can we predict, or that's in weight, can we predict from knowing somebody's height? And so the formula for the proportion of variance accounted for is, I'm going to go to the next page, is R squared. In just a second here, I'm going to have to format this. R squared, like that. R squared equals, no, don't do that. R squared equals, no, not super, text, not superscript, equals the proportion of variance accounted for. Oh, my word processor program just knows I want to make that capital, but I don't. R squared equals the proportion of variance accounted for. That is the proportion of all the variance in one variable that you can predict from knowing the other. So let's take our case. We had R equal to 0.8, right? So R squared is going to be equal to 0.8 times 0.8, which equals 0.64. 0.64. So what that means is 0.64 of the total variability in weight can be predicted from knowing somebody's height, but then we have to admit that the remaining variance, 36% of the total variance, cannot be predicted from knowing somebody's height. Now, similarly, you can also express the percentage of variance accounted for. And so the percentage of variance accounted for is 100% times R squared equals the percentage of variance accounted for. So in our problem up here, give this accounted for. So up here, our proportion was 0.64. We multiply that times 100%, and so we get 64%. 64% of the variance in weight is accounted for by knowing height. And then there's 36% we can't account for. So this is a way of expressing how good your prediction is of weight from knowing height. You're going to be pretty good at that because 64% of the variance can be accounted for. Now, let's take the case we talked about where we got a perfect correlation. Let's say that R was equal to positive 1.00, and this would be true and if R was negative 1.00, right? Well, then R squared would be equal to 1.00 times 1.00, which equals 1. Or in other words, 100%. That's right, 100%. So if two things are correlated 1 or negative 1, if there's a perfect correlation, like Fahrenheit and Celsius temperature are correlated positive 1 with one another, well, then that means you can account for the 100% of the variance in Fahrenheit temperature from knowing Celsius temperature. In other words, your prediction is going to be 100% right. You're going to perfectly predict Celsius temperature from Fahrenheit temperature. All right, so when people do correlational research, they will almost always report the proportion of variance accounted for, and that's all it is. They've just squared R to get the proportion of variance accounted for. All right, well, this will come up sometimes. I like to tell this story. Let me tell this story about some correlational research done by this professor at the University of Michigan. This was in like the early 1990s. At that point, and I know this is before most of you were born, but they were talking about installing V-chips in televisions. And a V-chip was essentially, and I guess they have them now, essentially a chip in the television that would allow parents to block certain programs. The program rating system like TVMA, and there's other ratings, I don't know what they are, came out of all this. And so depending on the rating of the show, the V-chip could block shows with a certain rating so that kids couldn't see them. And so that kind of the television industry didn't like this V-chip, and then other people did. And so there was a debate going on about whether the V-chip should be in the televisions, and I was living in Los Angeles at the time. And there was this debate on the radio where they gotten this professor from the University of Michigan who did correlational research. And he'd done studies on children's television watching and their effects on violent behavior. And he was debating this guy who was a representative from the CBS television network that didn't want the V-chips in. And so I'm going to try and reproduce this conversation for you. I like this story because I do the professor's guy's voice so well. If you ever meet him, you'll know him immediately because you'll say, oh, yeah, Dr. Gilbert did your voice. It sounded just like you. So this is like the stupidest conversation I've ever heard, I think. And when I go through this conversation, I want you to try and note all the stupid things that are said, and we'll try and go through them after it's over. Okay? But what the host of the show did was he asked the professor, Professor, could you describe your research on violent television? And the professor says, my research clearly shows that there is a correlation of 0.3 between the amount of violent television a child watches and the number of crimes the child is charged with prior to age 30. And what this means, in layman's terms, is that 10% of the violence in America is caused by violent television. Okay, and at this point, 30% of the violence in America is caused by violent television. That was his claim. Okay. Well, at this point, the guy from CBS breaks in, and I probably would have broken in too, but the guy from CBS did not say what I expected him to say. What the guy from CBS said, he said is, Professor, when you were counting the hours of violent television that the children watched, did you include the Three Stooges as being violent television? Oh, and this really made the professor mad. He got really angry and he said, Yes, I did include the Three Stooges. People say, what's wrong with the Three Stooges? They're just funny. Well, let me tell you something about the Three Stooges. Children who watch the Three Stooges before they're 8 are far more likely to have committed violent crimes by the time they're 30 than children who haven't. All right. Well, that's the end of the conversation. But brief as it was really, really stupid. Okay? And let's go back, and I want to look through the stupid things. First thing I want to talk about is, I'll put a little space here. The professor said he found a correlation of positive 0.3 between the amount of violent television a child watches and the number of crimes the child is charged with prior to age 30. And so that means there's a kind of a small positive relationship. What he found was that as violent television goes up, the number of crimes the child is charged with also tends to go up. Now, then he says that this means that 10% of the violence in America is caused by violent television. And the first question I have for you is, where do you think he got the 10% figure? Why does he say 10%? And if you remember what we just talked about, the idea is, well, let's take r squared. All right, if we square 0.3, we get 0.09. We get 0.09, right? So that would be 9%, not 10%. But that's, I'm not going to quibble about that. He rounded off. So 9%. But that's where the figure came from. He just squared the 0.3 to get the proportion of variance accounted for in this case, the number of crimes the child committed by knowing the amount of violent television the children watched. Now, here's the problem, and this is probably what you were thinking when I typed this up here. That's not the amount that was caused by violent television. That's only the amount that can be predicted. Okay? 10% can be predicted, and 10% would be the upper limit on what could be caused. That's the most that could be caused. And we know it could be 0, right? Because just because two things are correlated, it doesn't follow that there's a causal relationship between them. So, actually, before I listened to the professor guy, I thought, maybe watching violent television does make kids violent. But after listening to the professor guy, I'm not so sure. If you look at, say, crime in the early 1960s to now, it's like 5 times higher now, violent crime is, than it was in the 1960s. And so if violent television watching is only explaining at most 10% of that, well, then there must be a lot of other things going on. Other than that, it's a rather minor cause. It may not even be a cause at all. So that's what surprised me about the guy from CBS. I thought he was going to break in and say that, no, it doesn't follow that there is any sort of cause based on the correlational data that you presented. But he didn't say that. He asked about the Three Stooges and whether the professor counted the Three Stooges as violent television. Well, the guy from CBS did not make his argument particularly explicit, but if we were trying to make the argument explicit, I think it would go like this. He's saying, well, the Three Stooges, they're like cartoon violence or comic violence. Nobody's actually injured or hurt. There's no injuries or blood in a Three Stooges short. It's not like an Arnold Schwarzenegger movie or a bloody action movie. So you really shouldn't have counted the Three Stooges as being violent television in the same sense that, say, a war movie would be violent television. And so, because, Professor, you included the Three Stooges as violent television, well, that means your research is bad and we can't believe your research. Okay. Well, let's think about this and think through what the guy is saying. So he's saying that because you added this data, this bad Three Stooges data, that's what is responsible for the results that you got. However, it doesn't really matter what you think about the Three Stooges, whether you think they're violent television or not. Let's accept for the moment that, the Three Stooges aren't really violent television. So this professor, when he was computing his correlation, added a bunch of bad data to the correlation that he shouldn't have added. So this correlation has a bunch of bad data in it. Well, if you just threw in a bunch of bad data into a data set, what effect would that have on the correlation between the two sets of data? Would that tend to make the correlation higher if you threw in a bunch of bad data? Or would that tend to make the correlation lower if you threw in a bunch of bad data? And the answer is, if you threw in a bunch of bad data, that would make the correlation lower. Throwing in bad data would lower the correlation. So if the CBS guy is right, that all this Three Stooges data was really bad data that the professor threw into his data set, well, then if he were to redo his correlational research without the Three Stooges, the only possible thing that could happen is that the correlation goes up. It gets higher. So that's why that's a stupid criticism of that research. In fact, that is stupid criticism number one. You remember stupid criticism number one? Stupid criticism number one is that you can't criticize some research for having a lack of power if it found a reliable result. The professor found a reliable correlation here. So arguing he got this reliable correlation because he had a bunch of bad data in his data set, that doesn't make any sense. Having bad data would make the correlation non-reliable, but he found a reliable correlation, so that isn't a good argument. So the guy from CBS was dumb, and the professor guy was, I don't know if he's dumb, I don't think he's very ethical. I think he's going beyond what his data say. And of course, he would justify it to people saying, well, laymen won't understand the difference between causation and prediction, so that's why I said what I said. Well, that's an unethical thing to do. Okay, well, that's what I wanted to say about proportion of variance accounted for. So that may be a question on the exam where I'll tell you the correlation between two variables, and then you have to tell me what the proportion of variance accounted for is. Let's try one of these. So let's say that the correlation between a basketball player's height and the basketball player's number of rebounds is positive 0.2. What is the proportion of variance accounted for in rebounds by height? All right, so if the correlation is 0.2, we're going to square that, and 0.2 squared is 0.04, right? 0.04. So the proportion of variance accounted for in rebounds by height would be 0.04. Okay. All right, well, the next topic I wanted to deal with in correlation is, we've talked a number of times about how correlation can't be used to establish causation. We just talked about it here. But now the question is, why is that? So correlation cannot be used to establish causation because two reasons. Number one, it is sometimes unclear which variable is cause and which is effect. It is sometimes unclear which variable is cause and which is effect. This has a name. This is known as the directionality problem. The directionality problem. It is sometimes unclear which variable is cause and which is effect. An old textbook I used for this class a long time ago, they had a study that they described in the textbook that I presume is accurate. What they said was they had done a correlational study where they'd ask a group of several hundred college students, they'd ask them for their GPA, they'd also ask them how frequently they smoked marijuana, and they did a correlation on these two measures, people's GPA and how much marijuana they smoked. Now, before I reveal the results, what do you think? What correlation would you expect between amount of marijuana smoked and the grade somebody gets? Would you expect negative correlation, positive correlation, or no correlation between those variables? Let you think about it. Well, I would have said, just before looking at the data, well, I would guess there's a negative correlation that people who smoke marijuana more, well, they probably get lower grades. However, this study found a reliable but small positive correlation between amount of marijuana smoked and grades. That's right. For whatever reason, people who smoke marijuana tended to have slightly higher grades. Now, I would like to see this replicated, of course. I'm a little bit skeptical, I'll admit. This was with college students. I think I remember the guys in high school who did a lot of marijuana, and I don't think they were going to Harvard, so this may just be for college students. But all right, let's take it at face value that this is in fact correct, that there is a reliable positive correlation between marijuana smoking and people's GPA. Now, if that is the case, what could explain that correlation? Well, I can imagine several explanations. One is that maybe taking the marijuana calms people down before the tests, and so they have test anxiety, perhaps. And so that's what helps them get better grades. So it's possible that smoking the marijuana is causing the people to get good grades. But we can imagine it going the other way as well. Maybe what happens is these people go out and get good grades on tests, and because they get such good grades, they celebrate by smoking a lot of marijuana. So this correlation doesn't tell us very much. We don't know exactly which direction the causation goes. It could be that marijuana smoking causes good grades, or good grades cause marijuana smoking. The point is, just knowing the correlation doesn't tell us which way the causation goes. Now, I'm a student at Iowa State. In addition to being a professor at Iowa State, I've taken a lot of classes here. I'm an economics and math major, and I'm not taking any classes this semester, but I remember one semester when I was taking classes. It was when the state legislature was talking about potentially cutting the budget of the university. And so before class, the professor puts up this sheet showing, and puts it up on the screen at the front of the room. It showed the GDP per capita for a bunch of different countries. So GDP is the amount, gross domestic product. It's essentially the total amount value of the goods and services produced in a country during a year. And if you take GDP per capita, well, it's essentially a measure of how rich a country is, how much wealth is produced per person in a country. So GDP per capita, that's a measure of a country's wealth. And then the second column of data he had for all those countries, he also had how much money each country spent on education. And what you could see is there was this very strong relationship. Countries that had high GDPs, that were rich, spent a lot on education. Countries that had low GDPs per person, that were poor, spent very little on education. So it was pretty clear to our professor what was going on. If you wanted your country to be rich, well, you need to spend a lot on education, because it was the education spending that was causing the countries to be rich. And so it's crazy for the legislature to want to cut the university's budget. We want the university budget to be high if we want America to be rich. All right, well, I don't know. What do you think about this? Do you think of any other reason why rich countries might spend more on education than poor countries, other than it's the education that's causing them to become rich? Well, rich countries spend more on everything than poor countries. That's what makes them rich. So, of course, they're going to spend more on education than poor countries are. And so it could very well be it's the fact that they're rich is what's causing them to spend more on education, rather than spending more on education. It's what's causing them to become rich. I expect if we were to look at the amount of money each country spends on dog food, I bet rich countries spend way more on dog food than poor countries do. So what? If you want your country to be rich, you got to buy a lot of dog food? Surely not. Yeah. So, the point of this is, I don't know. I mean, the professor could be right. He could be right. Maybe it is education spending causing countries to be wealthy. Or he could be wrong. Maybe it's the fact that they're wealthy that's causing more education spending. Or it could be a little of both. Could be some of the reason they're rich is because they spent more on education, but could be that some of the reason they spent more on education is because they're rich. The thing is, if all you do is a correlation, you cannot know which way it goes. You can't know which was the cause and which was the effect. It can't tell you that. It can just tell you there's some sort of relationship here. Now you notice when I wrote the directionality problem, I say it is sometimes unclear which variable is cause and which is effect. Why did I say sometimes? Well, there are instances in which it is clear that one of the variables could not be the cause of another, particularly if the events that you're correlating take place at different points in time. So, if somebody gets drunk and then smashes their car into a tree, it is possible that drinking the alcohol is what caused the crash, right? But what is impossible is that the crash caused the drinking of the alcohol, because they drank the alcohol before the crash, so the crash couldn't have caused the alcohol drinking, but the alcohol drinking could have caused the crash. So that's why in that case we had a correlation. Well, that wouldn't suffer from the directionality problem. But the second problem is that a third unmeasured variable may be responsible for the relationship. This is known as the third variable problem. The third variable problem. And like the directionality problem that is only sometimes a problem, the third variable problem is always a problem. There was a article in the Iowa State Daily. This was a few years ago. And the title of the article, the headline was, Want Better Grades? Go to Class More. What the article reported was this correlational study that they'd done at some university. They'd just taken a whole bunch of variables that they thought might help determine what grade somebody gets in a class, like is the class in their major, how advanced is the class, does the class require a textbook, just a bunch of different variables about the class. And then they tried to correlate that with the grades that people got in the class when they were done. And what they found is, of all the different variables they studied, it was actually the percentage of classes that the student attended that was the best predictor of the grade that they got in the class. And so they presumed on that basis, that's what caused the people to get better grades, is that they're going to class more. So yes, going to class more causes you to get better grades because that was the highest correlated variable with GPA. Well, I don't know. Can you see any reason maybe why people who go to class a lot might get good grades other than it's because they go to class a lot? And I'll usually get people saying several things. One is, if you're more interested in the class, that would cause you to go. It would also cause you to do more studying and things. And so that could be why we'd expect somebody who's interested in the class to spend more time studying and to go to class more. And so it could be interest in the class that's actually responsible for the relationship. Some people are more responsible than others. They feel like they ought to go to class every day no matter what, as a sense of responsibility. Other people are less responsible. More responsible people are likely to do more things that would help them get a good grade, like study more and study better, I suppose. And so it could be responsibility is actually what is responsible for the relationship between the grade somebody gets and whether they go to class. Responsible person goes to class. Responsible person also does other things likely to get them a good grade. When I was at a family reunion not too many years ago, and one of my uncles is the deacon at his church. And his church started this program in the Colorado prison system, where they would go into the prison system and they would have a clergyman go into the prisons, and he had religious books and pamphlets. And then he would make the books and pamphlets available to any prisoners who wanted to, and any prisoners who wanted to talk to the clergyman, he made himself available to them. And they've been doing this program for like 10 years, and then they did a study afterwards to look at the effectiveness of the program. And so what they had found is that the recidivism rate, and this is the rate at which people go back to prison, the recidivism rate for the prisoners who'd been willing to take the religious books and pamphlets and talk to the clergyman was about half that of the general population in the Colorado prisons. And so, as far as my uncle was concerned, it was pretty clear what we needed to do about the crime problem in America. Just need to force the prisoners to go to church. That would solve it all. Okay? So he thought his program, the program his church was doing, is what was causing the lower recidivism rate, that the prisoners were not going back to prison as much because they were talking with the clergyman and reading the religious books and pamphlets. Well, can you think of any other reason why maybe the prisoners who were willing to talk to the clergyman would be less likely to have recidivism, go back to prison, than prisoners who weren't interested in talking to a clergyman or reading religious books? And I think a likely reason is, well, the more hardcore criminals who are planning to still be criminals would not probably be interested in talking to a clergyman. But the ones who are thinking of maybe turning over a new leaf or going good after they get out of prison, they would be the people more likely to be willing to talk to a clergyman and read religious books and pamphlets. So it very well could be that it was simply a desire to go straight, both caused the prisoners to be willing to talk to the clergyman and caused the prisoners not to commit crimes after they got out of jail. I offered that explanation to my uncle, and he didn't like it very much. Okay, so that's the third variable problem. There's some other variable that's causing these two variables to vary together. So it has to be, if you're going to come up with a third variable, it would have to be something that would cause the two variables you're studying to go in the same direction together, like a positive correlation, or in opposite directions, like a negative correlation. Okay, I got a article here, and I don't know if you'll be able to read it or not. Probably not. I'm going to read it for you. Let me see. Maybe I can blow it up. This was in the Christian Science Monitor a few years ago. I'll blow it up a little bit. And it doesn't, don't worry if you can't read it. I'll read it for you. Now, this appeared in the newspaper, and it talks about a correlational study. As we go through this correlational study, I want you to think of an alternative directionality explanation to what they are saying in this article, and I want you to think of an alternative third variable explanation to what they are saying in this article. Let's read it. It says, "No sex, please, we are athletes. According to a recent study by the Women's Sports Foundation, participating in sports may help high school girls make healthy choices about sex. The study found that teenage pregnancy rates were significantly lower for girls who participated in high school athletics than for those who didn't. Participating in high school sports gives girls a positive self-image and teaches them it's all right not to be passive. It teaches them that it's all right to say no to sexual advances," says Joan Medcore, chairman of the Women's Sports Foundation. The finding is expected to encourage greater funding for women's high school sports. Is that the answer to our reproductive woes? More money for women's sports? I'm a little bit skeptical. What they're saying here is that going out for sports is causing girls not to get pregnant. That is what they're saying. Going out for sports is causing girls not to get pregnant. Can you come up with another explanation for why teenage pregnancy is negatively correlated with going out for sports? And this is a directionality explanation. Other than it's going out for sports that's causing the girls not to get pregnant. All right, well, if you switch the directionality, maybe it's getting pregnant that's causing the girls not to go out for sports. That is, it's probably difficult to be competitive in the high jump during the latter stages of pregnancy. And so, if a girl gets pregnant, it's unlikely that she's going to go out for the sports team this semester when she's pregnant, I think. So, the correlation showing that pregnant girls are less likely to participate in sports than non pregnant girls. Well, I guess it could be the sports that's causing the lack of pregnancy or the lack of pregnancy that's causing the sports. Now, so that's one alternative explanation. Another alternative explanation, is there a third variable explanation that could explain why getting pregnant is negatively correlated with going out for sports? And a lot of times what I'll get students saying is, well, the amount of time that you have, there's only so much time in the day. So if somebody's spending time going out for sports, they have less time to get busy, shall we say, and so that might be. Also, let's think about poverty, for example. So poor girls are more likely to have teenage pregnancies than rich girls are. It's also the case that schools in poor school districts may be offering fewer sports, and also students may be in a position at poorer schools where they need to work after school in order to help support their families, and so they have less opportunity to go out for sports. So poverty could also be a variable that would cause girls to get pregnant, and poverty also might cause them not to go out for sports. So the finding that girls who get pregnant don't go out for sports as much, that really doesn't follow it's the sports that's causing the lack of pregnancy, right? Now, if we got journalists in the class, or aspiring journalists, this is the number one thing I think journalists don't realize. I subscribe to this website called Yahoo News Most Emailed Content, and so it lists the articles that people are passing around to one another. And almost every time I look at the list of articles, there's always a correlational study, or maybe one or two, where the writer is clearly trying to imply there's some sort of causal relationship between these variables that have been correlated, when really we certainly can't say that because of the third variable problem, or the directionality problem. So reporters in particular, I think, need to understand that correlation doesn't imply causation. So the third variable problem, unlike the directionality problem, that's always going to be a problem in correlational research. There is no way to eliminate the third variable problem as a possible explanation of the correlation that you got. So the take-home message from this section is, don't draw causal conclusions from correlational data. Don't draw causal conclusions from correlational data. Okay, well, we just talked about why you can't infer causation from correlation. Turns out that there are some mathematical limitations on correlations as well, and you should know about those. So here are the mathematical limitations of correlations. Mathematical limitations of correlation. All right, number one is poor at capturing non-linear relationships. Poor at capturing non-linear relationships. That's the first mathematical limitation I want to talk about. Okay, I don't use examples from cognitive psychology very much in class. Let me use an example here of cognitive psychology. There's a phenomenon in cognitive psychology known as the serial position effect. Serial position effect. Let me describe this for you. Let's say we had our class with like 80 people in it. And what I did is I got in front of the class and I read a list of 20 words one at a time. So dog, chair, car, so forth. Okay, 20 different words. And the people in the class are not allowed to write anything down. But as soon as I stop, as soon as I say the 20th word, they get out a pencil and they write down as many of the 20 words I've just said as they can remember. Okay, that's how the task goes. I read a list of 20 words, and then the people write down all the words that they remember. All right, so when you look at the data, the independent variable in this data is the serial position of the words on the list. And what I mean by that is, well, like dog was the first word, that serial position is 1, the second word was 2, down to 30. So this is kind of wild. You'd essentially have 30 levels of the independent variable in a study like this. So that's the position of the word on the list, the serial position. Then the other variable would be the percent of people who recalled each word. Okay, so what percentage of people recalled the first word on the list, what recalled the second. And what you get is, here's a graph showing you what that would look like. And it's a very strong effect. So serial position is down here. That's where the word was on the list. So first through 10th through 20th. And then percentage of people recalling that word could be nobody recalled it or could be everybody recalled it. Well, what you get is you get that people, the result you get is it looks like this. It looks like this curve here, where people, almost everybody's going to remember the first word and usually the second word. And then as you get towards the middle, people remember fewer and fewer words. The reason is you've had more time to rehearse these words to get them into your long-term memory, and so that's why it's easy to remember the early words on the list. But then what you see is that people start to get better near the ends. Almost everybody remembers the last word on the list, and that's usually the first word they write down. And that's because some of these words are still in your short-term memory, so you can pull them out of the short-term memory and do well on those. So you get this relationship here like this. Now, look at the graph here, and if we were to calculate the correlation between these two variables, serial position and percentage of people recalling, what would the correlation be? What would R be equal to? And the answer is R would be 0. That is, there would be, according to the R, no relationship between these variables, and that's because there's no tendency as our X variable, serial position, goes up, for the Y variable to go up or down. It's as equally likely to go up like here as it is to go down like here, and so there is no correlation between serial position and percentage of people recalling. So if all you did after that study was compute the correlation, you might go away thinking, wow, there is absolutely no relationship between serial position and percentage of people recalling. But in fact, there's a very, very strong relationship, one of the strongest relationships in psychology. It's just not a linear relationship. It's not a linear relationship between the variables. Okay, so that's what I mean by poor at capturing nonlinear relationships. Two variables can be strongly related in a non-linear way and produce a small correlation. Two variables can be strongly related in a non-linear way and produce a small correlation. That's what I mean by poor at capturing nonlinear relationships. All right, well, your solution to this when you're doing research is always draw a graph of the data to look for non-linear relationships. That is, if we draw on a graph of the data, we'd see clearly that there was a nonlinear relationship there. If we just did the correlation, we wouldn't be able to see it. So I would say you should never do correlational research without also accompanying it with a graph so that you can see what the actual relationship is between the variables. So maybe there's a nonlinear relationship there. All right. So point is, correlation is only good for expressing linear relationships. Two variables could be very strongly nonlinearly related and produce a low correlation. Number 2, greatly affected by extreme values. Greatly affected by extreme values. So if you've got some scores that lie far from the other scores in a data set, that can tend to have a big effect on the correlation. Let's go back to this graph that I showed you yesterday, if you'll recall. This is the graph of state area in square miles by state population. And it's probably a little bit hard to see the dots on the graph here. The correlation was really small. It was 0.08, which is not a reliable correlation. But if you could see the graph, you'll see most of the points, almost all of them, are clustered down here in the corner. And we've got these three extreme points out here. Most specifically, this one here. I don't know if you remember what this state is. This is Alaska. This is Alaska. It lies way far from the other points. So it is an outlying or extreme data point. And the question I have is, to what extent is this extreme data point here affecting our correlation? Now, this is a correlation. Realizes this isn't 0.8, it's 0.08. So this is a tiny correlation right now. It's not a statistically significant correlation. Well, what I did is I computed the correlation between state area and state population with Alaska included in the data, and then with Alaska taken out of the data. And so let's take a look-see at what I found. So with Alaska included, I'll put on the next line what I found. R was equal to positive 0.08, like I said. Our t-value had 48 degrees of freedom. It was equal to 0.61, and that p-value is greater than 0.05. So more than a 5% chance that the relationship was just due to chance. So we got a non-reliable correlation. All right, let's move on with Alaska excluded. Alaska taken out. Now R equals positive 0.39. Huge increase. Now T has 47 degrees of freedom, right? I lost a degree of freedom when I threw out Alaska. And so the T value is 2.89. And the P is less than 0.05. Now I get a reliable correlation. So that one data point, Alaska, was having a huge effect on the correlation, went from 0 to what I consider a moderate correlation of 0.39. Even a high correlation for psychology would be 0.39. So that's a pretty nice correlation there. But you can see Alaska was having a gargantuan amount of effect on the data. Made this non-reliable correlation reliable. Now, this is a case where an extreme data point made a correlation non-reliable, and if we threw it out, the correlation became reliable. It can go the other way, too. When I was in graduate school, I went to a talk by this guy who was presenting his research, and he showed the graph of his research. It was a scatter plot like the ones we've been looking at. And all his data points, except for one, were in this perfect tiny little circle. And as we talked about yesterday, if your data points are in a perfect tiny little circle, that means your correlation is 0. Okay? However, he had one data point that wasn't in the circle. It was way out in the upper right corner of the graph, way, way, way far from all the other data points in his data set. And that one point, because it was so far away from the others, was sufficient to give him a reliable positive correlation. And I'm sure that's how he reported it in his paper, too. Yep, there's a reliable positive correlation between these variables. But if you actually looked in the graph, there's pretty much no correlation between these variables. The entire correlation was just due to one outlying data point. So, what's the solution to this? Well, you should draw a scatter plot to look for extreme data points. Report the correlation with the extreme points included and with the extreme points excluded. Okay, solution. Draw a scatter plot to look for extreme data points. Report the correlation with the extreme points included and with the extreme data points excluded. All right, why do I say you should report the correlation with them included? Well, I think ethically you always should report the correlation of all your data. If you don't do that, problem is somebody, an unscrupulous researcher, can go in and you get to decide what the criteria are for calling a data point extreme. In our last one, we called Alaska extreme, but if we'd wanted to, we probably could have called Texas and California extreme as well, because they were extremely far from the other data points as well. And so by giving the opportunity to throw out data points, researchers could throw out data points that are inconsistent with their theory and just keep the ones that are. So that's why I think just ethically you need to report the correlation with all the data points included. Then you need to tell people, all right, it looked like we had some extreme data points. Here are the extreme data points that we saw, and we threw them out. And now here is the correlation with the extreme points excluded. And so that allows people to determine, okay, to what extent is the relationship between these variables due to the extreme data points. They don't necessarily affect the correlation. You might get the same correlation even with the extreme points taken out, but they certainly have the potential to. Okay? All right, so that was problem 2, greatly affected by extreme values. I'm sorry, this is mathematical limitation of correlations, number 2, greatly affected by extreme values. All right, let's look at number 3. This is the third mathematical limitation of correlation. Can be lowered by range restriction. Can be lowered by range restriction. All right, let's define this. What is range restriction? This occurs when there is a floor or ceiling effect on one of the variables in a correlation. Okay, can be lowered by range restriction. Range restriction occurs when there is a floor or ceiling effect on one of the variables in a correlation. So let's say you had 2 variables you were correlating, but one of them had reached the ceiling where it couldn't get any higher. If the range is restricted on one of the variables, the effect is going to be to lower the correlation. I want to put this underlined and in italics because I want you to know what the effects of range restriction would be. Range restriction would never cause a non-reliable correlation to become reliable. The only thing range restriction would do is reduce your correlation so you might not get a reliable correlation when you should have. Well, let me give you an example here. Okay, let's say we were looking at the amount people studied for a test, numbers of hours they studied, and then the number they got correct on the test. Why is it giving me 2 things? I don't know why it's doing that. All right, try and get it to not do that. There we go. Stop it. I don't know why it's doing that. All right, whatever. We'll just keep it like this. Okay. So here's hours of study down here. Is percent correct on the test. And let's say this is the data set we got. Now, look at the data from 0 to 10. 0 to 10. If we just calculated the correlation from 0 to 10, what do you think we'd get? Well, we got a perfect straight line from the lower left part of the graph to the upper right part of the graph. And if you got that, your correlation is positive 1.0. So the correlation is pretty much perfect between 0 and 10. But percentage correct, 100% is the highest you can get correct. And anybody who studies for more than 10 hours, well, they all get 100% correct, right? And so the correlation here between the variables is 0, right? Because it's totally flat over this section. So it was a perfect correlation until we hit the ceiling on the percent correct on the test, after which the correlation went way down. It goes to 0 after that. And in fact, the more data points we add after 10, the lower and lower and lower and lower the correlation is going to get. And that would make us think that there's not a relationship between these 2 variables, but in fact there is. The reason we got a low correlation is we have range restriction. You can't get higher than 100% on the test, so that's why it hits the ceiling now. And now every point we add at the ceiling is going to make our correlation lower and lower and lower. Okay, so, yeah. So now what's the solution to that? Solution, if possible, choose variables that will not show floor and ceiling effects. Always graph the data to look for range restriction. Always graph the data to look for range restriction. If it looks like you got a bunch of points like near the top of your scale or near the bottom of your scale all clustered there, that's a good suggestion. You got a floor or a ceiling effect there, and that is lowering your correlation. Okay? So those are the three mathematical limitations of correlations. Let's review very briefly. Sometimes unclear which variable is cause and which is effect. That's the directionality problem. Mathematical limitations of correlation. It's 1, it's poor at capturing nonlinear relationships. 2, greatly affected by extreme values. And 3, can be lowered by range restriction. Okay? All right, so the last thing I want to say, this is kind of my take-home message about correlation. Take-home message about correlation. Well, I think correlational research is some of the most important research that psychologists do, and I want to make the argument here for why it's important. So I want to argue correlational research is best used in 2 instances. Okay? Number 1, to solve practical problems requiring prediction. To solve practical problems requiring, let's spell things right, prediction. Okay. Well, let me explain what I mean. Remember, like the very first lecture we had in class, we said there are 2 good reasons to do research. One is theory testing, but the other is to solve practical problems. And this is where correlational research really shines, and some of the greatest contributions of scientific psychology have been correlational research precisely because of this. So I want to give you several examples here of important correlational research. One of the most important things that we do is psychologists make tests to predict how people will do well, how well people do in school or at their job. So the ACT test in particular, that was created, I don't know if you know this or not, it was created in the education college at the University of Iowa, created the ACT test. And it's not just Iowans that take the ACT test. I grew up in Kansas. I had to take the ACT test. Colleges in the Midwest generally prefer the ACT to the SAT. So lots and lots of people take the ACT test. Well, the purpose of the ACT test, the way it was developed is, it was developed so that your score on the ACT test would correlate as highly as possible with your college grades. So they did research where they had people answer a bunch of questions and then had them go through college and then look to see which questions on the test correlated best or most highly with how well people did in college with their college GPA, so it could be used as a predictor for that. Now, of course, nobody is saying that your ACT test causes your grades in college, and it certainly doesn't. That wouldn't make any sense. But because it correlates so highly with it, and the reason is probably because of these third variables, there's some combination of intelligence and experience that helps you do well on the ACT. That same combination of intelligence and experience helps you do well in college, and so that's why we can use the ACT test to predict how well you'll do in college. Now, another place that uses correlational research a lot is industrial organizational psychology. Industrial organizational psychology is often called IO psychology. I want to put in a plug, just like I put in a plug when I did the single subject designs about school psychology. If you're thinking about what to do with your degree and you're interested in working in business and you want a good salary, another one to consider is industrial organizational psychology. We don't have a program in that here. We do, there are places that do have programs in that. But even with just a master's degree, you can start working in business and get a really good job. It's one of the highest paying fields in psychology. And what you'd frequently be doing if you are an industrial organizational psychologist is developing tests that you can use to predict who would be the best at particular jobs. And that's really one of the great gifts that scientific psychology has given the world is these tests. And makes it much easier to hire the right person for the job if you've got a test that predicts their performance. Now again, nobody is saying that these tests you develop are causing their performance at work. No, that would be ridiculous, of course. But they correlate very highly with the performance at work, and so that's why they can be used to predict how well somebody will do at a particular job. And so developing tests for prediction, to predict, say, how somebody will do in school or at a job, that is one of the best uses of correlational research. Now, let's talk about school psych again. I talked about school psychology when we were talking about the single subject designs. And I told you then that some school psychologists, when they're doing research, use the single subject designs, but others do correlational studies. And we used to have a school psychology program in our department, and I remember one time we were interviewing to hire somebody for that program. And we had this one guy, what he had done is some correlational research, where he'd taken a bunch of variables, just pretty much every variable could think of, for kids when they were in third grade. And so they took things like their household income, whether the parents were divorced or not, how many brothers and sisters the kid had, how many younger brothers and sisters, how many older, just facts about how much income is in the neighborhood, whether the parents were divorced, just lots and lots and lots and lots of variables about these kids in third grade. All right, then he waited until they were in high school, and he got measures of how often they'd been suspended or had behavioral problems of some sort in high school. And then he correlated all of those variables in third grade with how many problems the kids had, behavioral problems, when they got to high school. I remember, I think the biggest predictor, the one that correlated most highly, was whether the kids had both parents in the home. Kids living in one-parent families more likely to get in trouble than those who weren't. Now, let's say that correlation is for real. He's not claiming that it's being in a broken home is causing the kids' behavioral problems. It may, or it may not. He doesn't care. What he just wants to do is to be able to predict for somebody in third grade how likely they are to have behavioral problems in high school so that he can intervene early. We can have some sort of intervention early to try and help those kids out. And so he didn't care whether any of those variables caused the behavioral problems or whether they didn't cause them. All he cared about is, do they predict these behavioral problems? Because if I can predict that this kid is going to have behavioral problems, then I can intervene early. So that's a very good use of correlational research as well. You're trying to predict now what kids are going to have problems in the future so we can do something about it now. So all the things I just described are some of the greatest gifts that scientific psychology has given to the world. The ACT test, very valuable at choosing people for a job, and then the job tests that psychologists developed are very valuable as well. All right, so that's one thing certainly that's good about correlational research. Now, the other thing that's good use for it, is to eliminate variables as the cause of a phenomenon. Okay, to eliminate variables as the cause of a phenomenon is the second one. And I'm going to underline this in italics it's too, because that's the point here. All right, what is this? I said that correlation doesn't establish causation. Well, what am I saying here is that you can eliminate factors as a cause using correlation. And that's right. Let's say that we've talked about how if two variables are correlated, that doesn't mean there can be a relationship between variables. That doesn't necessarily mean it's a causal relationship, right? We talked about a lot of cases today or there's a relationship, but maybe not a causal relationship. So it's possible for two variables to have a relationship, but not a causal relationship. But what is impossible is for two variables to have a causal relationship, but not to have a relationship. If there's a causal relationship between two variables, then there has to be a relationship between them. So let's take, for example, the study we talked about earlier with the guy from Michigan who was correlating the hours of violent television kids watched with the number of crimes they were charged with. Well, let's say he'd found a correlation of 0 between those two things. There's no correlation between how much violent television a kid watches and his later violent behavior. Well, then, we cannot conclude on that basis, or I guess we can conclude that watching the television is not causing the violent behavior, because if there is a causal relationship between those two variables, then they should be correlated. There should be a relationship between them. Remember, he found that the correlation was 0.3, which would explain 9% of the variance. 9% is the highest that could possibly be caused. And so that's why I think, based on his research, that there are probably more important causes than that. So, if you think there might be a causal relationship between variables, but you do correlational research, and you find there is in fact no relationship between them, it's not a reliable relationship, well, then you know there's not a causal relationship, because for there to be a causal relationship, there has to be a reliable correlation between the variables. Okay? So it's good for establishing what the limits are, how much one variable could have caused in the other. However, correlational research is not useful for establishing the variables that cause a phenomenon. Correlational research is not useful for establishing the variables that cause a phenomenon, only for eliminating variables as a cause. Okay, so long lecture today, but I finished off correlation. I did part I would typically do on Friday. So on Friday, the TA will be posting the within subjects variance test. It won't be very long, less than half an hour. So it was long today, but you get a short lecture on Friday, okay? So I'm going to work on getting the tests graded. And so look for your grade sometime today or maybe early tomorrow. And then I'm going to do, the next time I'll actually post a lecture after this one, is I'm going to do a review session on Monday. That would be April, today is the 1st, 2nd, 6th. And then we're going to have the test on April 8th. And I'll talk more about the test when I do my lecture on Monday, April the 6th. So I'll see you then.